Hi, welcome to my new video about graph neural network. In this video, we will learn what a graph neural network is, what are the different types of graphs, adjacency metrics, what happens inside a graph neural network like the node initiation, message passing, message aggregation, node updation, etc. And finally, we will see a simple basic architecture for a graph neural network. So let us get into the video. To understand about graph neural network, let us first see a very simple, interesting analogy about Sam. Here we have Sam, and here we have some features about Sam. Sam is a designer, 24 years, and he loves to sing. Sam is looking for a suitable match. Let us see how Sam does that. He first gathers information about his friends and friends of friends, and here we have a social interaction network of Sam. So here we have some friends of Sam with whom Sam is directly connected with, and some friends of friends with whom Sam is connected through these friends. So here we have some females, some males, and some of them are professors, students, engineer, designer, artists, etc. So let us see how Sam finds his perfect match. Sam first analyzes his features and he gathers information from his friends and he compares that features with his features and finally he finds his match. In a graph neural network also, similar thing happens. So let us see how we can relate this example with a graph neural network. This is a Sam's social interaction network, and here we have some people and there are some friendship connections and some features. So these features are written as a list. So we have a list of features, some friendship connections, and these people. So these people can be considered as the nodes of a graph, and the friendship connections can be considered as the edges of a graph, and the features like their gender, age, occupation, and their hobbies, those features can be considered as the features of a graph. So a graph neural network basically consists of these nodes, edges, and features. There are many more things, but now let us keep this simple. A graph neural network has these nodes, edges, and these features. Before knowing more about graph neural network, let us first understand what a graph data structure is. A graph is a collection of vertices and edges. These vertices are also called as nodes. These nodes or vertices are the information centers in a graph, and the edges are the channels through which this information flows from one node to its neighboring node. So here we have a graph with 5 vertices or nodes. These 5 vertices, some of these nodes are fully connected, like this node 1, 2, 3 are fully connected to each other, and some of these nodes are not connected, like the nodes 2 and 5 are not connected. So, a graph can be defined as a collection of vertices and edges, which is G equal to VE, where V is the set of vertices and E is the set of edges. There are many ways by which we can represent a graph. We can use adjacency lists, adjacency matrices, node features, edge features, etc. for representing a graph. But usually we represent a graph by using its adjacency matrix. Why is this adjacency matrix important? Adjacency matrix is the fundamental representation of a graph, and by looking into an adjacency matrix, we can tell whether two nodes in a graph are adjacent, which means whether they are connected by an edge or not. So, an adjacency matrix will be a square matrix of dimension V by V, where V is the number of nodes in the graph. Based on the direction of flow of information in a graph, we can classify the graphs into two types as directed graph and undirected graph. On the left, we have a directed graph, and on the right, we have an undirected graph. In a directed graph, we can see there is a particular direction in which the information flows. Here, the information flows from node 1 to node 2, 2 to 3, and 3 to 1. Whereas in an undirected graph, there is no particular direction for the flow of information. The information from node 1 flows to 2, and the information from node 2 flows to node 1 as well. Example, in a school, we have principal, teachers, and students. The principal can ask the teachers to do some work, and teachers can tell the students to do their homework. So there is a particular direction in which the information flows. there is a hierarchy. Similarly, in a directed graph, there is a particular direction for the flow of information. We can classify the graphs into two as weighted graph and unweighted graphs based on the weight of the edges. Here on the left bottom, we have a weighted graph, and on the right, we have an unweighted graph. So here we can see there are some numbers written on the edges of a weighted graph like 4, 7, 3. What are these numbers? These numbers are also called as the weights of this graph. So the edge between 1 and 2 has a weight of 4, the edge between 2 and 3 has a weight of 7, and the edge between 1 and 3 has a weight of 3. This weight tells us how important that edge is in the graph. So the edge between 1 and 3 has a weight of 3, and the edge between 2 and 3 has a weight of 7, which means that the edge between 2 and 3 is more important in this graph than the edge between 1 and 3. Whereas in an unweighted graph, there is no higher or lower weights. All the weights are equal in an unweighted graph. So the edge between 1 and 2 and the edge between 2 and 3 and the edge between 1 and 3 are having equal weights. Edge between 1 and 2 and the edge between 2 and 3 and the edge between 1 and 3 are having equal weights. So, since these weights are equal, we usually consider the weight of an unweighted graph as 1. Now, let us see how we can represent a graph in its adjacency matrix form. Here we have a directed graph with 3 nodes, 1, 2 and 3. And the information flow is from node 1 to node 2, node 2 to node 3 and node 3 to node 1. So, wherever there is an edge or wherever there is a flow of information, then we write 1 in the matrix, and wherever there is no edge or no flow of information, we write 0. As I said, the dimension of the adjacency matrix will be V by V, where V is the number of nodes in the graph. Here we have a graph with 3 nodes, so the dimension of the adjacency matrix will be 3 by 3. So here we have a square matrix of 3 by 3 dimension, and we have V1, V2 and V3. Now let us fill this checkerboard. There is no edge between vertex 1 and 1. So between 1 and 1, we write a 0. There is an edge between vertex 1 and 2. The information flows from vertex 1 to vertex 2. So from 1 to 2, we write 1. There is no information flowing from vertex 1 to vertex 3. This direction is very important. So there is no information flowing from vertex 1 to vertex 3. So we write 0. Now consider this node 2. There is no information flowing from node 2 to node 1. So we write a 0 here. There is no information from node 2 to node 2. So again from node 2 to node 2 we write a 0, and there is information flowing from node 2 to node 3. So we have an edge here. So we write from node 2 to node 3, 1. Now consider this node 3. There is an information flowing from node 3 to node 1. So there is a edge here. So we write 1. There is no information flowing from node 3 to node 2. So we have 0 between node 3 and node 2. And there is no information flowing from node 3 to node 3. We don't have an edge here. So again 0. Easy. Now here we have an undirected graph. So let us see how we can represent this graph in its adjacency matrix. So we have V1, V2, V3. Now let us fill this. There is no edge between node 1 and 1. So between 1 and 1 we have a 0. There is an edge between nodes 1 and 2. So between 1 and 2 we have a 1. And there is an edge between node 1 and 3. So between 1 and 3 we have 1. Now consider this node 2. There is an edge between node 2 and 1. So between 2 and 1 we have a 1 here. There is no edge between 2 and 2. So between 2 and 2 we have a 0. And there is an edge between 2 and 3. So between 2 and 3 again we have a 1. Now consider this node 3. There is an edge between nodes 3 and 1. So we have a 1 here. There is an edge between node 3 and 2. So we have a 1 again here, and there is no edge between 3 and 3. So finally we have a 0. It is very easy, right? Now, if we look at this adjacency matrix, we can find something very interesting. Can you notice something? This adjacency matrix of this undirected graph is a symmetric one. So, it is interesting, right? The information flowing from node 1 and node 2 and node 2 and node 1 are the same. Similarly, the edge between 2 and 3 carries the information from node 2 to node 3 and node 3 to node 2. Similarly, there is an edge between 1 and 3 carrying information from 1 to 3 and 3 to 1. So the information flow is bidirectional here, and this makes this adjacency matrix symmetric. Now we have a weighted graph with 3 nodes. So this is a weighted graph and this is a directed graph. And here the weight between node 1 and 2, the weight of the edge between nodes 1 and 2 is 4, between 2 and 3 is 7, and between 1 and 3 is 3. Now let us fill this checkerboard. So between 1 and 1, we do not have an edge. So we have a 0 here. The only change happens here is for an unweighted graph, we considered the weight as 1. All the weights of all the edges was considered as 1. So wherever there was an edge, we wrote 1 there. Here, instead of writing 1, wherever there is an edge, we write the weight of that edge there. So there is an information flowing from node 1 to node 2. So there is an edge here and the weight of that edge is 4. So between node 1 and node 2, we write 4. There is no edge between node 1 and node 3. There is no information flowing from 1 to 3. This direction is important. So we write a 0 here and consider this node 2. There is no information flowing from 2 to 1. So we have 0 here. There is no information flowing from node 2 to node 2. So again, we have a 0 here. And from node 2 to node 3, there is an edge and weight of that edge is 7. So we have a 7 here. Now consider this node 3. There is an edge between node 3 and 1 with a weight 3. So we have between 3 and 1, we have 3. Now there is no edge between nodes 3 and 2. There is no information flowing from 3 to 2. So we have 0. And there is no edge between 3 and 3. So again we have 0. This is very easy to write the adjacency matrix of a graph. Recently, a group of researchers at MIT discovered a new class of antibiotics. So, this discovery of new antibiotic halicin was done by using graph neural network and explainable AI. So, this antibiotic can kill the bacteria and pathogen which was resistant to almost all classes of antibiotics. So, this antibiotic resistance was a problem that the researchers and scientists were dealing with for many years, and with the help of graph neural network, these researchers could solve that problem. So, why do we need a graph neural network? So, traditional neural networks can deal with data like images and text which belongs to the data called as Euclidean data. Here, this image can be considered as a grid structure. Here, the pixels can be considered as the grid, and the distance between these points can be calculated by calculating the Euclidean distance between these points. Whereas many real-world problems cannot be considered as this Euclidean data or this grid-like structure. So these non-Euclidean data can be modeled as a graph, and we can train this graph to make many amazing predictions, and we can do many different tasks by using these graphs. So, for example, the people in a social network, or the atoms in a molecule, or the amino acids in a protein, these are the examples of non-Euclidean data which cannot be considered as a grid, or we cannot directly calculate the distance between 2 points in these scenarios. So all these non-Euclidean structures can be modeled as a graph, and we can train this graph neural network to predict different things in this graph. So where is this graph data used? Companies like Facebook, LinkedIn, and Twitter, they model their graph as users in their platform, and they analyze the social interaction and the relationship of these users, and they recommend personalized content. Companies like Amazon, Netflix, and YouTube, they model user item interactions and make personalized recommendations. Companies like Google and Microsoft, they use knowledge graphs to organize and connect structured data. So as I said, we can perform many tasks by using graph neural network. These tasks can be classified into three as node level tasks, edge level tasks, and graph level tasks. Let us see each of that in detail. So this is an example for a node level task. This is a node classification task, and here we have a graph with 5 vertices. So some of these vertices or nodes are labeled and some of these nodes are not labeled. So these labeled nodes are smokers and non-smokers. So these smokers and non-smokers make a pattern or a network here, and based on the interaction of the labeled nodes, we are going to predict or classify this unlabeled node. So a node exists here, but we do not know the label of this node. Based on the pattern of interaction of the other nodes, we can classify this unlabeled node, and we can tell whether this node is a smoker or a non-smoker. Similarly, in an e-commerce platform, there are users and items. So the nodes of this graph are users and items in an e-commerce platform. We know a node exists here, but we do not know the label of that node. So by analyzing the pattern of interaction of other nodes, we can easily predict whether this node is a user or an item. So all this can be done by using graph neural network. So this is a node level classification task which we can do by using graph neural network. Next, this is an edge level task. So this is an edge prediction task. So here we have this e-commerce platform network, and we have users and items. So these users and items are interacting with each other. So if we can predict the edge formation between these two nodes, between this user and item, then we can tell whether this user and item will interact. So if we can predict the probability of such an edge formation, then we can recommend the product to that users, and we can advertise that products, and we can improve the recommendation system, and we can improve the sales in that platform. So this is an example for edge prediction task which can be done by using graph neural network. Now this is an example for a graph level task. So this is a protein, and the protein is composed of different molecules or different amino acid chains. So by analyzing this graph and the pattern of the amino acid sequence in this graph, we can predict or we can classify this protein and tell to which class this protein belongs to. So this is an example for a graph level task. Now let us learn what happens in a graph neural network. Here we have a very interesting story about 4 friends. So these 4 friends, 1, 2, 3 and 4 are planning for a trip, and they have not finalized their destination yet. So let us see how they are finalizing their destination. So the friend 1 takes a paper and writes his preferred location on that paper. And then after writing that, he passes that paper to friend 2. Now friend 2 reads the location written by friend 1, and based on that, he updates his preferred location on that paper. And then he passes that paper to 3. Now 3 reads the locations written by 1 and 2, and based on that, 3 updates his preferred location, and then he passes that paper to friend 4. Now friend 4 gets to know all these locations written by friends 1, 2 and 3, and based on that, he writes his preferred location, and he summarizes that and he reads that out. And they finalize this location like this. So how can we compare this with the graph neural network? Suppose these 4 friends are the nodes of the graph neural network, and the message or the paper they passed was the message or the message function, and the destinations written on that paper are the features of this graph. So, like the friend 1 passed his paper to friend 2 by writing his feature, and based on that, friend 2 updated his preferred location and wrote on that paper and passed to friend 3 and friend 3 to friend 4, and they summarized this location. Nodes in a graph passes their information to their neighboring nodes, and based on that, these nodes update their information. So these 4 friends are the nodes of this graph, and the paper being passed is the message function, and the destinations written on that paper are the features. So each node passes the message to the neighboring node, and based on the received information, the neighboring node updates its feature and passes to the next neighboring node. This continues until all these nodes receive the information and they update their features. Now let us see what happens in a graph neural network. Here we have 4 friends, and there is a vector associated with each of these 4 friends. So the friend 1 has a vector of A213, 2 has a vector of B421, 3 C322, and D134. So these 4 friends form the nodes of this social network, and they have this feature vector associated with them. The first step a graph neural network does is it converts these vectors into nodes. This step is called as node initiation. So we have 4 friends as the nodes of this network, and these 4 feature vector is converted into the nodes of this graph neural network. So the node 1 is A213, node 2 is B421, node 3 is 322, and node 4 is D134. So after initiating these nodes, the next step, message passing, happens. So we now know what message passing is. So let us see how that is done among these 4 friends. Okay. So A passes its feature vector 213 to its neighboring nodes B and C. B passes its feature vector 421 to its neighboring nodes A and D. C passes its feature vector 322 to its neighboring node A, and D passes its feature vector 134 to its neighboring node B. Now all these 4 nodes passed its feature vector to its neighboring nodes. So this was message passing. So after message passing, all these nodes passed its feature vectors to its neighboring nodes, and all the nodes received its feature vector from its neighboring nodes. So the next step happens, message aggregation. Now A received its features from B and C. So now A has its feature vector 213, and it received features B421 and C322. Now A calculates its aggregated message by calculating the average of these 3 vectors. So the aggregated message is 2 plus 4 plus 3 by 3, 1 plus 2 plus 2 by 3, 3 plus 1 plus 2 by 3, which is 3, 1.6 and 2. Next, B received its features from A and D. So B calculates its aggregated message as 4 plus 2 plus 1 by 3, 2 plus 1 plus 3 by 3, 1 plus 3 plus 4 by 3, which is 2.3, 2 and 2.6. Now C received its message from A. So C now has the features of C and A, which is C322 and A213. So the aggregated message of C is 3 plus 2 by 2, 2 plus 1 by 2 and 2 plus 3 by 2, which is 2.5, 1.5 and 2.5. And D received its message from B, So D has D134 and B421 with D, and D calculates its aggregated message as 1 plus 4 by 2, 3 plus 2 by 2, and 4 plus 1 by 2, which is 2.5, 2.5, and 2.5. Now, all the nodes passed its messages to its neighboring nodes, received its messages from the neighboring nodes, and after receiving, it calculated its aggregated message. Now, the final step happens, which is node updation. So, initially, the nodes were having the features A213, which changed to A3 1.6 and 2, B421, which changed to B2.3, 2, and 2.6, D134, which changed to 2.5, 2.5, 2.5, C322, which changed to 2.5, 1.5, and 2.5. So this final step is called as node updation. So all these nodes updated its features. So let us summarize what happens in a graph neural network. First, the graph neural network initiated the nodes by converting the features into nodes, and after that all the nodes passed its features to its neighboring nodes, which is called as message passing, and after receiving, all these nodes calculated the aggregated messages, and after that they updated their nodes. So this happens in one hidden layer of a graph neural network. So the input of this hidden layer was the features of that graph, and after that the nodes were initiated, and it calculated the aggregated message, and finally it updated the nodes. So this happens in one hidden layer of a graph neural network. Like this, there will be multiple hidden layers. So this process iterates over multiple layers. So we have an input layer here with these features, and we have multiple hidden layers, and the output can be node embedding, edge embedding, or graph embedding, depending on our task, whether the task is a node level task, like in the example of smokers and non-smokers, or an edge level task, like the edge prediction in an e-commerce platform, or it is a graph level task, like classifying to which family that protein belongs to. So depending on these tasks, and depending on whether our train setting is supervised, which means whether we know the labels of that graph, semi-supervised, like in the example of smokers and non-smokers, we had some of the nodes labeled and some of the nodes not labeled, or unsupervised, where all the labels are unlabeled. So depending on this train setting and different tasks, we will decide our output, whether it is a node embedding or edge embedding or a graph embedding. So basically we have an input layer with this social network graphs features, and we have multiple hidden layers, and finally we have the output. So from this video we learned what a graph data structure is, different types of graphs, directed, undirected, weighted, non-weighted, how to calculate the adjacency metrics, different tasks with graphs like the node level task, edge level task, and graph level task, what happens in a graph neural network, the message passing, node initiation, node updation, message aggregation, etc. And we also saw a simple architecture of graph neural network. Hope this video was helpful. Thank you.